Okay, so welcome to Math 150, multivariable calculus. This is lecture 22. So what I want to do today is I want to talk about the chain rule. I want to talk about optimization in the second derivative test. So we've already covered a lot of this earlier when we were doing the method of least squares and finding the best fit line. We actually already talked about a lot of the issues with optimization in several variables. So this is something I'm really trying to do in the classes, have multiple passes on the material so that when you see a new concept, it's not the only time you're going to see it. We'll see it once, we'll see an application, and we'll see it again. We've seen a little bit of the multivariable chain rule. We've seen it in the special case when we're traveling along a specific path. You can do things in greater generality. So what I'm going to do today is I'm going to first state the multivariable chain rule. I'll do an application of it, then we'll go to optimization in several variables. And then with whatever time we have left after all your questions have been answered, we'll do as much as we can about the proofs of why the multivariable chain rule works. We proved it in the special case of a path. It's not that much worse to do in general. This is a problem where linear algebra would be extremely useful. The more linear algebra you know, the better you can formulate what's going on, and the more clean, the more concise the statements are. When you look at some of the results in optimization in several variables, there is just no good way to explain why the hell this is true without knowing some linear algebra. It just seems absurd, these various conditions. Oh, so if all this happens, then this happens. Where does this come from? When you know some linear algebra, it explains where things go on. So I will teach you just enough linear algebra to understand what's going on in 2 dimensions. There is a generalization to higher dimensions. You need to know a little bit more linear algebra for that. We can, of course, ignore all the linear algebra, and I can just give you some strange conditions to memorize. I have no desire to do that. I'm sure you have no desire for me to do that. We're on the same page here. If you take linear algebra, this will hopefully be something that they will cover. All right. So we talked a little bit last time about what goes on if we're on some path R of t. I like to use C of t for curve. The book likes to use R of t. If we have some function f of several variables, R of t is going to be our point in space. Maybe it's x of t, y of t, z of t. And when I look at f of R of t, this is now just a function of one variable. So it has derivatives. So what I could do is I could call g of t being f of R of t. And then I could have g prime of t, which is dg dt. So that is just a Calc 1 problem, which we know how to do. What we want to do is we want to say, imagine we know very easily the derivatives of r with respect to time, and we know very easily the derivatives of f with respect to x, y, and z. Can we somehow combine that knowledge and get the derivative of this function g, which is f of r of t, in terms of our knowledge of the derivatives of f and our knowledge of the derivatives of r? And that's what the chain rule for paths allows us to do. It converts this problem of this composition of functions to 2 simpler problems. What we would have to do if we didn't have this rule is we would have to take our function f, shove in x of t, y of t, z of t, expand everything out, have this monster mess in terms of t, and then differentiate that with respect to t. We can do that. But it's often simpler not to have to do that and just say, hey, we can expand it out, and we have the following. So writing it very explicitly, the gradient of f is df dx df dy. And the subscript r of t just means that's the point where we evaluate it. When you're doing the chain rule, you always need to make sure you evaluate things at the right point. So when I'm evaluating f is always evaluated at r of t, so its derivatives are evaluated at r of t. Similarly, my function r is always evaluated at t, so the derivatives of r are always evaluated at t. So the derivative of r is just x prime of t, y prime of t, and so we're just taking the dot product. And the nice thing about this is at the end of the day, this is going to just be a number. Well, it's got to be a number. If you look at what this is the derivative of the function f of r of t. F of r of t, this is just a function that takes t as an input and gives you a number as an output. So its derivative should just be a number. So at the end of the day, I have to have a number. The gradient of f is a vector. R prime of t is a vector. How can I get a number from 2 vectors? The dot product. So this is a very natural thing to do. Also, in the special case, when f has just one variable x and r has just one component x, this reduces to just df dx dx dt, which is the one variable chain rule. Right? If r of t is just the function x of t and f depends only on x, there's no y, then it's just df dx dx dt. Okay? So whenever we see anything in multivariable calculus, we always want to test and see, does this reduce to something we've seen before? And in this case, it does. Well, what if I had three components? If I had three components, it would be very similar. I would now just have a df dz and a z prime of t. And when I expand everything out, I just get a third term, df dz dz dt. And so this would be the chain rule when I have my function f composed with the function r, where r depends only on one variable. Well, I could have r depend on more variables as well. I could have r depend on, say, t and s. And then I could ask, what's the derivative of f of r of ts? Well, now that I've got the derivative of f of r of t of s, you always have to ask the question, with respect to what? So if r depends on two variables t and s, what are my possibilities for the derivative of f of r of ts? What could I take the derivative with respect to? So I give you f composed with r, and r is evaluated as a function of two variables at t and s. What are the two variables I could differentiate with respect to? T and s. So this is what's going on if I take the derivative of my function with respect to t. Well, when we take partial derivatives, the way you take partial derivatives is you pretend the other variable is doing nothing. So why not just pretend that we have another variable? Let's just pretend that r depends on t and s. And instead of saying d by dt, let's just say partial with respect to t. And there you go. And that's the multivariable chain rule. That's all we really need to do, is just pretend that there's another variable along for the ride and keep it fixed. And if we keep it fixed, then we just have a curve in one variable. So there's lots of different ways of trying to represent and write what's going on. So the biggest issue is, do you write the letter S and then T, or T and then S? Why do you think they do ST? Alphabetical order. So a lot of people will do ST because that's alphabetical order. Sometimes people do TS because we've done T first, then we're adding S as the second variable. Does it matter which we do? No. Just be careful and look and see how things are being done. So there's a couple of different ways of doing it. So if I have my function f, and f depends on three variables, say x, y, and z, and x, y, and z depend on two variables s and t, I can take the partials of f with respect to s, or I could take the partial of f with respect to t. And I get df ds is df dx dx ds plus df dy dy ds plus df dz dz ds. That's essentially what we had a moment ago. The only difference is, instead of using a regular d that we've seen all of our life, we're now using this partial d. Or I could take the partial of f with respect to t, and the only thing that changes now is I replace dx ds with dx dt, and so on and so on. So there's a couple of ways that people like to write this. So one is, you start off with the function f at the top, and then the next level are the variables that f depends on, x, y, and z. And then the next level below that are the variables that x, y, and z depend on. And so you can see each of x, y, and z each depend on s and t. So writing it really explicitly, here's f, and to get here, I do df dx, df dy, df dz. To get from here to here, I do dx ds, here's dy ds. To get here, dx dt, dy dt, and so on and so on. And so if I want to figure out what is the derivative of f with respect to s, I look at all the paths that start at f and end at s. And I multiply as I go down a path, and then I add up all the paths. And here's my df dx times dx ds, here's my df dy times dy ds, and finally my df dz dz ds. So this is just a nice way to remember how you get to the chain rule. Morally, you might think, well, if I have df dx dx dt, can I just cancel the dx and call that df dt? Well, if I do that, why am I having x's and not y's and not z's? This is basically saying, look at all the different ways this could happen. So this is essentially a very nice generalization of what we did for paths. If I had more variables, if I had STU, I would just have something else down here. If I had more variables here, I could have maybe W, X, Y, Z. It just makes the equations more involved. This is why we have, or one of the reasons why we have linear algebra. So that as you start to have more and more involved expressions like this, with products like this, we can write it down in nice vector form or matrix form. Who are my physics students? Have you done special relativity? Have you done Einstein's summation convention? So again, you often introduce things to try to make the formulas readable. And you want to find nice, compact ways of saying what's going on. So for problems like this, there's typically two ways to do things. One is to substitute for x, y, and z as functions of s and t, put that into f, and then just differentiate directly with respect to s and t. The other is to use these formulas and say, well, if I can calculate the derivative of f with respect to x and the derivative of x with respect to t, that gives me that first piece, and then I just do this for the other two. The two approaches should give you the same answer. On an exam, I might ask you to do it both ways. Do you think one way will be easier than the other? Probably. Why would I have you do it both ways? Yes. So one way is to just substitute for x, y, and z as functions of s and t, plug them into f, and just differentiate directly as a function of s and t. The other is to use the chain rule. Why might I ask you to do it both ways? So different methods, because sometimes one is used in the other. So there will probably be some times when you can't plug in, but there's another reason why I will have you do it both ways. What should you get when you do it two different ways? The same answer. What if you don't get the same answer? You did at least one thing wrong. Both of them could also be wrong. It's possible that you got both methods wrong. What if they both match? No. No. No, you could have actually made two different mistakes. I have one paper in math where I actually made infinitely many mistakes, but they all canceled. It was a sign error. And so it was an integration by parts, and I dropped the minus sign. The boundary terms vanished, but I always integrated by parts an even number of times. And so since the boundary terms vanished, I was off by a factor of -1 to the 2n, so it was okay. So I've had a couple of situations in life where all my mistakes have canceled. It is possible you could have the same answer from both methods, but you did two completely different mistakes and got the same wrong answer. Just because you get the same answer doesn't mean that you're right. Do you have more confidence if you get the same answer two different ways? Yes, but it's not a proof that you're right. If you have two different answers, it is a proof that you have at least one mistake. All right. So in a complete shocker, this is the general version of the chain rule. This is pretty good notation. So they're using x1 through xn as the variables of f, and they're using t1 through tm as the variables that the x's depend on. And what's nice about this is we don't run out of letters in the alphabet. If I do, s and t, at some point I'm going to start hitting into the x, y, and z, and so I'll just do it df, dx1, dtk, all the way up to df, dxn, dxn, dtk. All right, so let's do an example. So I hear we have somebody visiting who's learning polar coordinates, so let's do something involving polar coordinates. So can somebody give me the formulas for x and y in polar coordinates? Cosine theta and sine theta. So I can write, if I want x as a function of r and theta as r cosine theta, I can write y as a function of r and theta as r sine theta. What would the partial of x with respect to r be? So if I take the derivative of x with respect to r, what would that equal? It would just be cosine theta. What about the derivative of x with respect to theta? What would that be? Negative r sine theta. And I'll do the derivative of y with respect to r would just be sine theta. The derivative of y with respect to theta would just be r cosine theta. That's not a great R over there, so I'll leave it like that. Okay, so let's say I give you maybe the function f of x, y is x cubed plus xy minus y squared. And I want to find d by d theta of f of x of r theta, y of r theta. Okay. So there's two methods. So option one, f of x of r theta, y of r theta would just be x cubed. So that'll be r cubed cosine cubed theta plus r squared cosine theta sine theta minus r squared sine theta. Right? Oh, sorry, sine squared theta. I just plugged in what x is and what y is. X is r cosine theta. Y is r sine theta. So the x cubed becomes r cubed cosine cubed theta. The xy becomes r squared cosine theta sine theta. And the y squared becomes r squared sine squared theta. How would I differentiate this with respect to theta? Yeah, just take the derivative with respect to theta. Now, when you're taking the derivative of this, some terms are going to be easier than others to take the derivative of. So my daughter likes to note that d by d theta of sine squared theta is just sine 2 theta, that you just move the 2 down. My daughter's in 8th grade. Is this correct? So you doubt my daughter. All right, so let's check. D by d theta of sine squared theta, what does that equal to? 2 sine theta cosine theta. And what is 2 sine theta cosine theta equals? Equals sine 2 theta. Don't doubt my daughter, please, okay? This is one of the issues with trig, right? Depending on what I give you, I can write the same thing many different ways. The derivative of sine squared theta is sine of 2 theta. It's also 2 sine theta cosine theta. So depending on what I give you in terms of how I express it, I can write my answer in very different ways. Now, if I justify the argument by saying that the way the derivative works is you pull the 2 down and it goes from being an exponent, well, do you think that that's going to be the derivative of cosine cubed? That's just going to be cosine of 3 theta. I'm not playing Simon Says now. I'm not saying Kayla says that. I'm asking you right now, do you think the derivative of cosine cubed is cosine of 3 theta? How would you check it? Yeah, expand it out. And then when you have your 2 formulas, you could just evaluate it at some different points. And as long as you can find one point where they're not the same, then you know it's not. So if I take the derivative of cosine cubed of theta, that should be 3 cosine squared of theta, and the derivative of cosine is minus sine of theta. This is enough to show that it's not going to be cosine of 3 theta. Just take theta equals 0. If you take theta equals 0, -3 cosine squared theta sine of theta is 0, but cosine of 3 theta is 1. So this does not always work. How would you take the derivative of cosine theta sine theta? How would you take the derivative of that term? So one is you could use the product rule. How else could you take the derivative? Yeah, this is 1/2 of sine of 2 theta. Might have been the reason why I was doing this over here, to try to prime you all. If you know your trig identities, if you know your algebra identities, you can often make your life easier. Do you have to make your life easier? No, you can use the product rule. The product rule is not terrible, but if you happen to remember that this is just 1/2 sine of 2 theta, then you'll make your life a little bit easier. And so when you try to compare things at the end of the day, if I use the angle addition formula, or if I use the product rule, I'm going to get a slightly different expression. And it may not be clear what the answer is. Okay, what if I try to calculate df dx? What's df dx?
Uh, 3x squared plus y.
Plus y. And then if I do df dx at the point x of r theta, y of r theta, that would just be 3r squared cosine squared theta plus r sine of theta. We already know df, I'm sorry, not df. We already know dx d theta is just minus r sine theta. So the df dx dx d theta piece is just going to become 3r squared cosine squared theta plus r sine theta times minus, so I'll put the minus over here, r sine theta. And that would just be the df d x dx d theta piece. Then you would do the df dy d theta. So as an exercise, I want you to finish doing this problem at home. Do it both ways. Do it if you want, use the product rule, use the angle formula, and see which for you is easier. Again, trying to show that two things are the same could be quite challenging. The best thesis defense start at the history of Williams College was one of my thesis students, Jake Levinson, years ago, where he was trying to prove two expressions were the same. And the first expression filled up half the page, and the other expression filled up the other half of the page. He said, well, to make it easier, let's expand both. And it takes 20 pages to expand the top half. Page 21 was an equal sign, and then the next 20 pages was expanding the bottom, with the end from Spaceballs. If you can read this, you don't need glasses. And so it's, how do you show this nightmare is the same? Depending on how you do calculations, you might actually think you got it wrong one way, but you might actually have the right answer. Depending on how you're doing the calculation, the answer can look different. Just because they look different does not mean they're different. One of the best ways to see if they're the same or not is just choose some values. Put in some values for r and theta. And if they happen to keep equaling the same number, then they might be the same. And the more numbers that they're the same, especially if you're just choosing random numbers, almost surely they're the same if they're always equal. This is why I gave you this stupid, let's just pull down the 2 from the exponent to the multiple of the angle. Well, it actually turns out it is justifiable. And if we try to think that, does that work over here as well? No, and the easiest way to see it is just take theta equals 0. So again, when you're doing these calculations, there are two different ways we can do this. One is I can view my function as a function of r and theta. I can't really call it f of r and theta because f is a function of x and y. So I need some new name. So we might call maybe script f or italics f of r theta might be f of x of r theta, y of r theta. So I might do something like that. I can't use the same function because my function f is a function of x and y. More generally, imagine f was a function of x, y, and z. I clearly can't have little f then being a function of r and theta because f needs 3 inputs in that case. So this is a way to take the fact that we know dx dr, we know dy dr, we know dx d theta, we know all of these, and we only have to do that calculation once. So if my function is easy to work with in terms of x and y, there's really no need to go to the pain of plugging in everything in terms of r and theta, expanding it out. If the function is easy to differentiate with respect to x and y, keep it like that. So you can imagine I could give you really nasty things in terms of x and y. Since I'm at the board, I don't want to do that. But that's the advantage. All we have to do now is we have these conversion factors, the dx dr, dx d theta, and so on and so on. It's a one-time calculation. You should remember it. You'll probably not. You're probably not going to memorize it. Is it easy to rederive? Yes. Right? It's not that hard to derive. Well, if x equals r cosine theta, okay, dx dr is just cosine theta. So yes, I should really remember it, but I can rederive it so fast, it's not a big deal. And that's the whole point of the multivariable chain rule, is you take a problem that, yeah, maybe you could shove everything in and make it a function of just r and theta, but it would be unpleasant to do the derivatives. And now we can just reduce it to a simpler problem. All right, so that is the multivariable chain rule. All right, so now what I want to shift to is trying to find extreme values, trying to find maxima and minima, or candidates for maxima and minima. A lot of times we can't do what we want to do, so we back off and say, okay, I can't do this, what can I do? For many problems in life, the goal is to maximize something. Imagine you own American Airlines. What is your objective? It should be to maximize profit. If it's not your objective, there's some issues, right? For almost any company. What if you own a baseball team? What is your objective? Not necessarily. What else could be your objective if you own, say, a major league sports team? To win the championship. And you might be willing to take a loss because you have pride in your city or you want to just have the championship. But it's trying to figure out, what are you trying to optimize? It may not be money. For a lot of things, it's money. There are some professional athletes who take pay cuts because they're on teams and leagues with salary caps. And like, well, look, I've got enough money. I'd rather have a title. I'll take less money so that we have more money available to sign other people. So for many problems, especially in economics, you are trying to optimize revenue or something along those lines. But it may not always be what you're trying to optimize. So we're trying to figure out how to optimize various things. When you were trying to decide on where to go to college, what were you trying to optimize? This is probably not something to talk about while the camera is on and things are being recorded. But when you're making a decision, why did you choose Williams? What was it about Williams that you felt would be worth doing? I'm advising a lot of students right now on where should they go to graduate school, and what are you trying to optimize? Some graduate schools are giving higher stipends than others, but they may not be as strong of a program. Okay, so let's say we have a function of 2 variables. You can, of course, generalize this to several variables. And we want to try to figure out, does it have an extremum, a local maximum or minimum at some point? And so it's going to have a maximum at the point AB if you take any point nearby and you can't be larger. That's what f of xy less equal to f of AB. And this is just a disk. That means just if you're sufficiently close, I draw some circle around my input AB. And then that means any xy in that disk of radius r centered at the point AB, the value of my function is no larger than the value of the function at AB. So it doesn't mean that it's strictly less. Can somebody give me a very simple function that has a maximum at the point 1, 2? Function of 2 variables that has a maximum at the point 1, 2. Simplest function you can think of. It doesn't have to be the largest function. It doesn't mean every other point is less than this. It just means no point is greater. What's the simplest function you can think of that would have a maximum at the point 1, 2 by this definition? I'm sorry?
Y equals 2.
What's supposed to be a function of x and y. So f of x, y equals, I'm sorry? But then why does that have a maximum at 1, 2? If it's 1 plus 2x, what's the simplest function you can think of? F of x, y equals, what's the simplest function you can think of? Everybody's got to be speaking now. Easiest function to analyze. F of x, y equals, I'm sorry?
X.
There's something even simpler than x. Simplest function, 0, or any constant, right? Any constant function. Any constant function would have a local max or local minimum everywhere. So that's, always think about what are my simplest functions? Simplest functions are constants. The next simplest would be linear functions, something x plus something y. Then you would start adding quadratic terms and cubic terms and higher terms. So if I just take a constant function, it will have a local maximum everywhere. It will have a local minimum everywhere. If I want to try to find something that has a local max at the point 1, 2, let's consider f of x, y equals negative x minus 1 squared minus y minus 2 squared. What's the value of this function at the point 1, 2? So it's just 0. And if I take anything other than 1, 2, either x minus 1 is non-zero or y minus 2 is non-zero. Since I'm squaring them, neither of these could ever be negative. So if I'm not at the point 1, 2, at least one of the terms is positive. And so this function is going to have a local maximum at the point 1, 2. And in fact, if I move any distance from the point 1, 2, I will be strictly less. So you can always try to come up with some examples in your mind to get a sense of what's going on. So we say a point is a critical point if the partial derivatives vanish at that point. So they also talk about the partial derivatives not existing. So for the most part, we will deal with cases where the partial derivatives exist. Why? We're trying to use calculus. If we're using calculus, what do we need to be able to do? Derive. We have to be able to take derivatives. So if we're in situations where the partial derivatives don't exist, we can't use the techniques from calculus. So for us, we will always be working in the situations where the partial derivatives exist. And this goes back to Calc 1. How do you find your candidates for local maximum or minimum? Well, I look for places where my first derivative is 0. If the first derivative is positive, then that means my speed is increasing. So if I let a little bit more time go by, I've gone further. If I go back in time, I haven't gone as far. Is there anything else I have to look for to find maximum and minimum? Endpoints. If you're running to see where am I running the fastest? I don't want to do this holding the iPad. As I slam into the wall, that might be where I'm traveling the fastest. I'm just not allowing myself to look at time beyond that. So I have to check endpoints. Are there a lot of endpoints you need to worry about in Calc 1? How many endpoints might you have to worry about? What's the worst case? 2. Not a big deal. In several variables, however, you could actually have an entire boundary. I might want to say, I want to look at a function defined on a unit disk. So on the boundary and inside, where's the function largest? So I have to look at what's going on inside, and I have to look at what's going on the boundary. And now I have infinitely many points to look at. And so multivariable calculus becomes a lot harder. We will learn how to deal with that on Wednesday. So a critical point is a place where the partials are 0. We talked about this when we did the method of least squares. We had our error function. We were trying to find the best fit values. And we said that the candidates were going to be where the partial derivatives vanish. And the reason is if you just hold one variable constant and just move in the other one, well, then it's a one variable problem. And in a one variable problem, if you want to be at a local max or minimum, your first derivative has to be 0. If your first derivative is 0, must you have a maximum or minimum at that point? Or can you have the first derivative be 0 without having a maximum or minimum? What do you think? Does anybody remember the function that's really bad? Do you remember the nasty function? Yes. So x cubed has no max or min at x equals 0. And the reason why this has no max or min at x equals 0 is even though the first derivative is 0, f prime of x is 3x squared, f prime of 0 equals 0, but the second derivative is 6x, and the second derivative is also 0. And that's what causes the problem. Just because the first derivative is 0 doesn't mean you have a maximum or minimum. It means you have a candidate. Well, when you think about what's going on, if I have infinitely many points to check, and I can somehow use calculus to reduce that infinite number to a small finite number, that's progress. It's okay if it gives me a couple of points that don't work out. The idea is it's pruned the list of what I have to look at. And because it's pruned the list of what I have to look at, it's okay. Now I just need more sophisticated tests. Well, we have the first derivative test from calculus, where if the first derivative is positive on one side and negative on the other, that means it's coming down and coming up, we must have a minimum. Similarly, if it's positive on one side and then negative on the other, it's increasing then decreasing, we have a maximum. So we do have the first derivative test that requires us to understand the sign of the first derivative in a small neighborhood of the critical point. We also have the second derivative test. And the second derivative test says if the second derivative is positive, it's a min. If the second derivative is negative, it's a max. Notice it says nothing about what happens when the second derivative is 0. If the second derivative is 0, you actually have to look at the third derivative if it exists. Or if the third derivative is 0, you have to look at the fourth derivative. And you have to start playing games like that. All right. So what I want to do here is just state the second derivative test in multivariable calculus. This is probably where you should scratch your head the most. You know, if I have a function of 2 variables and I have a critical point, then it all comes down to this quantity. So it's the second derivative of f with respect to x squared times the second derivative of f with respect to y squared minus the square of the second derivative of f with respect to x and y. So I'm going to assume I'm in a case, assume all derivatives are continuous. So fxy equals fyx, so that the mixed partials are the same. This is the key quantity we need to look at to see if we have a maximum or minimum. If you look at it, some of this looks similar to the second derivative test we're used to. We do have things involving second derivatives. It's just there's now more than one second derivative. I can take 2 derivatives with respect to x, I can take 2 derivatives with respect to y, or I could take a derivative with respect to x and then y, or a derivative with respect to y and then x. And it's telling us this is the quantity we look at. And then here is what goes on. So we let d equal this quantity. So d is equal to fxx fyy minus fxy squared. If d is greater than 0, then we have a local. Oh wait, did things get shifted down? Oh, okay. And so I'm going to just leave it here. And I'm going to just talk about another way of looking at this. This is in the book. You can look at the book to see exactly how they phrase it and whatnot. To me, this is gobbledygook as to why do we look at something like this. And so I want to try to explain where this comes from for the last couple of minutes. Let's go back to a function of one variable. Where should we have our critical point? Where do you want to have the critical point located? At x equals 0. Let's make life easy for us. So assume critical point without loss of generality at x equals 0. Without loss of generality, let's assume f of 0 equals what? We're trying to find out if we have a maximum or minimum. Without loss of generality, what can we assume the value of f of 0 equals? 0, right? If f of 0 equals 5, we just shifted everything by 5. Let's make life easy. Let's assume f of 0 equals 0. So we can write Taylor series. F of x is equal to f of 0 plus f prime of 0 times x plus f double prime of 0 x squared over 2 factorial plus dot, 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 dot. So f of x would be equal to f double prime of 0 x squared over 2 factorial plus dot, dot, dot. If x is small, x cubed is much smaller than x squared. So we get f of x is approximately f double prime of 0 x squared over 2 factorial. So if our function has a Taylor series, or if we can at least approximate it, we can always adjust things so that f of 0 is 0. We're just shifting everything up or down. We can always translate so that our point is the point 0, just to make things easy. So if x is really small, my function looks like f double prime of 0 over 2 times x squared. So let's look at two very special parabolas. Let's look at a of x is x squared, and let's look at b of x is negative x squared. So here, a prime of x is 2x, a double prime of x is 2, a double prime of the critical point 0 is 2, is just positive. Here, b prime of x is negative 2x, b double prime of x is negative 2, b double prime of 0 is negative 2 is less than 0. I always forget the second derivative test. I always forget, does positive mean it's a minimum or maximum? So what I always do is I always say, well, look, I know there is such a thing as the second derivative test, and I know it involves the sign of the second derivative. I just can't remember if positive means maximum or positive means minimum. But I am so close to knowing what I'm supposed to. Well, if I just choose a specific function where I know if it has a maximum or minimum, I say, oh, let me take the function x squared. I see the second derivative is positive. That's clearly a minimum. Oh, okay, so if the second derivative is positive at the critical point, we have a minimum. Similarly, if the second derivative is negative, we have a maximum. So this is the second derivative test. What it's basically saying is, if I have a critical point, so my first derivative is 0, essentially my function looks like a constant, which doesn't matter, plus a parabola in a small neighborhood of the critical point. So if the coefficient of the parabola is positive, it's a minimum. If it's negative, it's a maximum. Okay. If the second derivative is 0, then all of a sudden I have to start looking at the cubic term. And if the third derivative is 0, then I have to look at the quartic term. That's the second derivative test. Okay. So what we want to do now is we want to look at a multivariable Taylor series. And so now you can see why we spent some time at the beginning of the semester talking about sequences and series, talking about Taylor series. Now, we haven't proven multivariable Taylor series formulas yet. So let's think a little bit. What do you want your point to be? Which point should we look at? X, y equals what? So what should our point be with, which is going to be our critical point? 0, 0. And what should the function be at the point 0, 0? It should be 0. Let's just make life simple. Okay, this is just without loss of generality. Now the gradient is, the gradient of f, which is, df dx, df dy, and the gradient of f at the point 0, 0 is 0, 0 at the critical point. Okay. So this is now the question of how do we expand? So if I give you my function f of x, y, it should be f of 0, 0. The next piece is going to be the gradient of f at 0, 0 dotted with x, y. The gradient of f is a vector. X, y is a vector. When I take the dot product, I'm going to get a number. That's going to basically tell me how much I'm moving to first order. And now this is where things get interesting. Plus, it's going to be 1/2 xy Hessian of f at 0, 0 xy. With the Hessian matrix, I'm sorry?
What matrix?
The Hessian. This is not related to the soldiers in the Revolutionary War. So this is going to be fxx, fxy, fxy, fyy. And these would all be at 0, 0. Okay. And so when I expand this out, this is going to give me a number. Okay. This gives a number. Right. So let's see what we would actually get if we start expanding things out. So I have 1/2 xy fxx, fxy, fxy, fyy, xy. So I have to do my matrix multiplication. It's xy, and then I'm going to get fxx times x, fxy times y, with a plus fxy times x plus fxy times y. Then when I multiply them out, it's basically like a dot product again. I'm going to get 1/2 fxx times x squared plus fxy xy plus fxy x squared. No, sorry, x times y plus f. Oh, and this one is, sorry, this one should be fyy plus fyy y squared. And so when I multiply this out, I get 1/2 fxx times x squared. I've got 2 with the 1/2, so I'm going to get fxy times xy plus fyy over 2y squared. And if you think about it, we're trying to approximate our function f of xy. If you look at the second derivative, if I take the derivative of this twice with respect to x, what do I get? 2 derivatives with respect to x, we get fxx. That's exactly what we should be getting. If I take 2 derivatives with respect to y, we get fxy. 1 derivative with respect to x, 1 with respect to y, we should be getting fxy, and we do. If I take 1, we get. So it turns out this expression over here looks a lot like what our function should look like. And now we have 1 minute left, or actually half a minute. Can anybody tell me there's a name for fxx, fyy minus fxy squared when you have a matrix like this? What is that number? The determinant. So we'll talk a little bit more about that just to motivate. That's where this expression comes from. It's the determinant of the matrix. It's essentially saying if you change variables nicely, that's what's going to tell you whether or not it's maximum or minimum. All right, so this is a good place to stop.